And we're going to record this so you can watch it back at home if you ever need to. All right. My first slide is just reviewing our first couple of definitions of what makes something an acid or what makes something a base. Now, again, we had old scientists that figured these things out. The Arrhenius definition of an acid is something that creates hydronium in solution. You're not going to be asked what's the Arrhenius definition. The Bronsted-Lowry is dealing with donating a proton. A base, on the other hand, creates hydroxide in solution or accepts a proton. What I want to do is let you take a minute to write that down, and then I want to switch to the Smart Notebook, and I want to draw out an example of that. We're one slide down, one to go. All right, so when we think acid, the most common acid is hydrochloric acid. I'm going to do Lewis dot reaction here to show you how this works. Two definitions of an acid. One is it creates hydronium in solution. So if I were to draw the hydronium ion, what's created from this reaction between HCl and water, does anyone know why I would have a plus charge on it?
Got rid of an electron.
Yeah, formal charge of +1 on that oxygen. There's only 5 electrons around the oxygen, normally has 6. Remember formal charge from last unit or last semester? It's good stuff. So this would be the products of that reaction. But how did we get there? I want to kind of go over that with you really quickly here. This end of oxygen is partially negative. This end of HCl is partially positive. Opposite charges can attract one another. As a matter of fact, they can attract each other enough where you can get this pair of electrons creating a bond with that H in HCl. Remember when we did our activation energy curves, at the top of the peak there's that kind of activation complex where both things are kind of melded together before they break apart? That's kind of what's happening here. You have water and HCl bumping into each other in solution. These opposite charges can attract each other enough where those two electrons could create a bond there. However, hydrogen is unstable if it's bonded twice. After all, it only has one valence electron. So this bond breaks and just forms these two electrons around the Cl. This, I think, does a good job of demonstrating those first two definitions of what makes something an acid. Yes, it creates hydronium, that H3O plus that I have on the product side. But an acid is something that donates a proton, an H plus. And HCl gave its H plus away to the water. The other reason why I like this leading into what we have to go over on that second slide, when acids no longer look like acids, is water plays a role in a lot of this. The idea of water interacting with something else can make something become an acid or a base. So water does play an important role in that. If I go do an example of a base, I'm going to do the most common weak base of ammonia, NH3. Why did I draw the double arrow this time?
Because it's a weak base.
Because it's a weak base. You don't do a single arrow for a weak base because it only partially dissociates. First definition of what makes something a base, it creates hydroxide in solution. Well, I can draw the Lewis dot for that. And in this case, the other product is going to be ammonium, polyatomic ion. The ammonium is a +1 because it only has 4 electrons directly around the nitrogen. It should have 5, so it has a formal charge of +1. So the first definition of a base, something that creates hydroxide in solution, I showed that by writing this equation. Second definition of what makes something a base, it accepts a proton. Once again, partial negative end of the molecule, partial positive end of the molecule. molecules just bumping into each other, all of a sudden attraction takes over. This pair of electrons on the ammonia can create a bond with that hydrogen. Once again, the hydrogen's now bonded to two things that's unstable. This bond will break. Remember, every bond is composed of 2 electrons, so now there are 4 electrons, or 2 more electrons being donated to that oxygen to give us the products there. So I like kind of showing you the Lewis dot of this to start off with, just to give you a reminder of what makes something an acid, what makes something a base that we've talked about before. Because we want to remember that, in particular, the role that water plays in this. Because as we move on to our last slide here, we get into what's called the Lewis definition of acids and bases. The Lewis definition is this first bullet point. An acid is something that accepts a pair of electrons. Each definition of an acid, starting with the Arrhenius definition, which is the oldest definition, then the Bronsted-Lowry, a little more recent after that, then the Lewis definition. As far as I know, it's the same guy that did Lewis dot. I mean, it kind of makes sense based upon the definition. They try to expand what makes something an acid. So instead of having a narrow, this is the only thing that can be an acid, there's more things that can behave like an acid. So really that second bullet point is why I wrote up on the board, you don't look like an acid. Well, acids don't have to have hydrogen. I know it's the easiest way to identify it if it starts with a hydrogen, but not everything that's acidic has a hydrogen. For example, things that don't have enough electrons. Remember when I mentioned formal charge before? Oh, that's going to be brought up with things that are electron deficient. They're not at the octet. Polar double bonds. Carbon dioxide is a good example of that. I'll show you that one in a minute. Metal ions is the one that I have just clipped out from the textbook. So the textbook actually shows this. Iron plus 3, for example, a metal with a high charge can attract a whole bunch of these, and what will happen is one of these bonds will eventually break. That causes the electron pairs in OH bond to be pulled even closer to the oxygen than normal. That makes the oxygen atoms even more positive than they normally are. So if that's really partial positive, it can be attracted by a separate water, pulled away, and all of a sudden it makes hydronium. Being able to explain why some of these things make an acidic solution is not something you're going to have to do. Being able to identify that this makes an acidic solution is something you have to do. For those of you who took chemistry last year, we did a new lab. It was a stoichiometry lab where we took aluminum foil and we put it in a copper solution. Does anyone remember that? And then you had to filter it out, and the shiny aluminum turned into copper because it was a single displacement reaction. When me and Mr. Butters were first testing out that brand new lab, we started noticing bubbles. I'm like, wait a minute. Copper chloride plus aluminum should not be making bubbles because that's single displacement. There's no gas in that. It kind of threw me off for a while. And then I started thinking about it more, that solid aluminum is becoming an aluminum ion in solution. That aluminum ion is doing exactly the same thing this iron ion is. And in fact, it's acting like an acid, and it's creating some acid in solution. And then that acid is doing a secondary reaction to create hydrogen gas, and then we were getting some bubbles. It was one of those, here's the main reaction that we're doing, students. Ignore the bubbles, because we don't want to try to explain that to Chem 1. Because quite frankly, in AP, it's kind of hard to understand at first. But it was that another example of we made an acidic solution, even though we had no acids to start with. As for a base, quite frankly, the Lewis definition focuses a lot more on acids than it does on bases. Bases accept a pair of electrons. And there's not a lot of good examples out there of that, but today you're going to see examples of ions that act as a base because of how they interact with water. So I'm going to go back to Smart Notebook here. First off, a Lewis acid accepts a pair of electrons. That's happening right here. Chlorine only had the 6 pairs of electrons here. Now it has 8. It took a pair from the water. A Lewis base donates a pair of electrons. That's happening right here. So these definitions that I'm giving you aren't changing what we already thought. It's just expanding beyond things that we typically thought were the only things that could be acids or the only things that could be bases. The example I put on there to begin with was boron BOH3. Notice how boron is not at the octet. But boron only had 3 valence electrons, so the best it could do is pair up 3 times. But if this was in the presence of water, this could create another bond. That's why it could make a BOH4. Now, if this oxygen creates another bond with that boron, one of these hydrogens, let's call it this one, is going to become a little unstable, and it's going to be released. It's going to be donated. So even though the boron part isn't giving or taking a hydrogen, its interaction with water is going to cause it to become acidic. Carbon dioxide. Remember dry ice that we played with? Polar double bonds are susceptible to reacting with water. Carbon dioxide has 2 polar bonds. Now granted, the 2 cancel each other out, so it's nonpolar overall. That idea of symmetry that we talked about in the bonding units first semester. Once this bond is created here, though, there'd be 5 bonds for carbon. Carbon can't disobey the octet rule. It's not in the 3rd energy level. So this bond can break. When that bond breaks, I now have extra electrons around that oxygen. What will happen is, once again, this can break off, just like it did in the previous example. And to make carbonic acid, then, we could have these extra hydrogens either coming onto that O there, or they'd just right away be donated into solution. Because if I drew the Lewis dot for carbonic acid, excluding the electrons, sorry, this is a double bond right here. This would be the Lewis dot for carbonic acid, H2CO3. The goal of today isn't to know how to draw this stuff out like I did. Although I like drawing it out for a couple of reasons. It's trying to show you how all the definitions still work for even the old stuff, like the HCl that we did. Secondly, I don't know what Ms. Schaefer remembers from organic chemistry, but I remember doing this all the time, mechanisms of how does this react with that and what takes the place of this and that. And it was something that always kind of fascinated me about chemistry. I had a hard organic chemistry teacher, because when you go to college, you'll learn, hey, take it with this person if you want to get this grade, take it with this person if you want to get that grade. Hey, that person's the one who wrote the textbook, so do you want to take it with that person or not? I always took it from the person who was the hardest, because I wanted to learn the most, and this is what she did all the time. Iva Reich, I even remember her name, and I bet she remembers my name because she had a photographic memory. You say your name once in a lecture hall of 400 students, she knows who you are at that point. It's the first person I ever met that was like that. But we go over this today because we need to look at things that don't normally seem like acids or seem like bases.